of when an area could change. Everybody see what we did there? If you need to actually use Faraday's law to determine the magnitude of an EMF, you need to express whatever's changing in terms of its variables that are changing in time. You need to express it as a function of time. Any questions about that? Okay. So now we've determined a couple things. We've determined the EMF induced in this loop. We've determined the direction of the current flow. But something else is going to be interesting here. So let's ask ourselves, what are the forces on the individual legs of this thing? First of all, let me ask you, what is the total net force on that structure?
0.
0. Why?
It's enclosed.
Because the magnetic force on any closed loop of current is always identically 0. Right? That's it always sums up to 0. But that's not to say that there's nothing interesting happening here, because let's ask ourselves what would be happening here. So there's going to be a force on this guy, which is going to be counteracted by a force on this guy. There's going to be a force on this leg, which will be counteracted by a force on this leg. But because of the physical arrangement, these three legs, they don't care. But this guy is going to care. Specifically, whoever's pulling him to the right is going to care, because he's going to feel a resistive force. Let's try to pull it back to the left. Well, I say to the left. Let's see if we can reason right through that. I've got a current direction now and a field. I need to use the right-hand rule for fields. Yeah. Forces. I need to use the right-hand rule for forces, which is fingers in the direction of the current. That's straight down. Curl them towards the field, which is coming out of the board. So I'm going to scoot my hand over like this and curl them towards out of the board. Stick out my thumb, and I get a force vector that is this way. And again, that will be counteracted by another force vector over here. So the net force on the structure is 0. But in this case, it does make a difference to whatever is pulling this to the right. It feels resistance, right? This is, in fact, magnetic braking. So if you've ever wondered how you stop a maglev train, this is it, right? How do you stop a train? Well, brakes. Brakes, what do brakes do? Apply friction to a wheel that then stops the wheel. But a maglev train doesn't have any wheels, right? If you don't know what a maglev train is, it's a magnetic levitation train. They have several places in Asia. How do you stop it? You don't have, friction doesn't work. There's nothing touching a rail. Here, magnetic braking. Through clever application of changing magnetic fields through, or constant magnetic fields through changing areas. It doesn't really matter. You're going to get the force either way, right? So this is magnetic braking. It actually occurs in many situations. I'll show you a demo next time we're here. But that force, while it's balanced out with the force on the other side, will serve to drain energy out from whatever is pulling this thing to the right. It works kind of like friction. It's not friction, but it works like friction in that case. Make some sense? All right. Now, I set this up for you saying that you are physically, or something is physically moving the bar to the right, and therefore the flux changes and you get all this stuff, right? It is possible to leave it without the velocity to the right. Just set it up to where it's static, and then by other means manipulate the strength of the field. In other words, the area wouldn't be changing then, the strength of the field would be changing. What would that do? Well, if you do it right, it'll induce a current no matter what, because you have a changing field. But if you do it right, you actually can get a force here that will accelerate this rod to the right. Right? And then if you have ends of this thing over here off of which the rod can slide, you now created a projectile. In the Navy, they call it a railgun. Right? That's what this is. I have a really small one here. It's not really a railgun, but it's the idea. So what this is a coil of wire. You can see it's copper here. It's shielded, so is insulated with some clear plastic. But I'm going to press a switch, and there's going to be a current that flows through the wire. This is a big bundle of steel rods. So what's happening is when there's a current in the wire, we know, well, this is a solenoid, first of all. We know what the field of a solenoid looks like. It goes right up or down the center of the solenoid. What these iron rods start to do is then take that field and allow it to propagate all in this entire space, right? So because iron is ferromagnetic, the magnetic field produced in the core gets into the rods of iron, to put it crudely, and then that enables this whole thing to act like a magnet, the field of which will represent whatever's happening in the coil. So when I flip a switch, I start the current. So that's a change, right? Right now there's no flux through this coil. There's no there's no magnetic field due to this coil. But when I flip the switch, then there is a field, because then there's a current. The current takes a little bit to ramp up. That's a changing field, right? So then if I put something on it, like this little aluminum ring, there's now, now there's no flux because there's no field. But when I press the switch, there's a changing field, which means there's a changing flux, which means nature will try to counteract it by inducing a current in this ring, right, to try to counteract the change in flux, just like it did in the thing that I raised where they're falling down. But because this ring is free to move, that current will then experience a force due to the magnetic field, and cool things happen. Right? This is just a railgun. It's really small. No big deal. Right? I can do it with a larger one. Same thing's going to happen. It's just not going to go as high because it doesn't have it has more mass. Right? These might be different materials. Oh, that goes a lot higher. Okay, so this is fair enough. So that's not a mass issue. These are different materials. I'm actually not sure. This is aluminum. I'm not sure what this is. It's something different. They do have different mass, but what's happening is I'm inducing a greater current here because of the conductivity thing. Yeah. So, but the same idea, right? Here's a copper one. This has more mass. Greater conductivity, but more mass, doesn't go quite as high. That's the idea. This one, you can't really see it, but there's a gap, right? So I don't form a closed loop. There's no opportunity for the current to flow. There is a current flowing, I should point out, but it flows around and then hits the gap and goes down and flows the other way around the other side. So I have opposing currents, which means that forces will cancel. So that one doesn't actually do anything. But I can do other things with that, right? Here's a light bulb that's connected to a coil. There's a coil in here. So, what can I do? Well, if I change the current through this coil by starting it, that produces a change in flux through this rod, which is now passed through the coil, produces a change in flux, which then produces a current in the coil and creates a light bulb. I know it's right. But the whole reason that's happening is because there's a change in flux through this coil that's connected to the light bulb. It turns this coil into sort of a battery. I can do other cool things, right? It doesn't just have to be coils. Here's a copper tube, right? And here, here's a little steel ball. So I need somebody to come catch this. I need a volunteer. Come on, I control your grades, and I know you're. Come on. So, please, John, just come catch it. Right? I'm going to drop this steel ball down this copper tube. Just to put your hand above and catch it. Right? Lower it a little bit so they can see it come out. Perfect. All right. So if I asked you how long it would take for this ball to reach the end, you could do that. This is the kinematics problem. You can measure this, figure that out. No big deal. And here we go. Right? Not very long. Let me do it again. Just normal steel ball down a copper tube. Okay? Thank you. We hand these out. Now, this is not a normal steel ball. This is a magnet. All right, same thing.
You can hear it like cycling through a little bit.
Yeah, how do we explain this? Well, you can imagine this tube as a set of rings, right? And so as the magnet moves down, there's a change in flux, which produces a current flowing around this copper tube, which then the magnet will interact with, producing a braking force, just like this one, right? Thank you. So it takes a long time to get down because of that. Nothing magic about it, it's just magnetic forces. Okay, questions about any of that? These are cool. They have a really large one in the McLean Science Center in Birmingham, if you've ever been there. It like launches it up to the ceiling. It's really cool. It's in a tube, so you can't get to it, but other than that, it's cool. Alright, questions about any of that? Alright. A few minutes left. Okay. So what we have seen is some induction problems involving a changing field, and we've seen them involving a changing area, but that's not the only way flux can change. Remember what the flux is. NAV cosine theta. This comes right out of the dot product, right? The flux is B vector dot A vector, the magnetic flux that is. The B dot A gives you the cosine theta when you unpack it for the definition. Okay, well in general, if I would like to know the EMF, I'm going to have to take a derivative of this, right? Assuming that this would be expressed as a function of time. So let's ask ourselves, what would it look like if I had a loop of conducting material and the field wasn't changing, the area of the loop wasn't changing, but that this angle was changing? Specifically, I'm going to let the loop rotate, right? So that the angle between the B field and the A field are constantly changing. In other words, theta now is a function of time, right? I'm not going to, well, sure, I will. I'll write it here. Where theta is equal to theta, not times t, it's as a function of time. I don't know the specific function, that would be case specific, but it's a function of time, it's changing. If that's the case, d phi dt looks like this. Well, if theta is the only thing changing, n, a, and b are all constant, so they come out of the derivative. And then I've got the derivative of the cosine of theta, which is what? We'll leave off the negative sign for now, like you always wanted to in calculus. I gave you permission to leave off the negative sign for this derivation. All we're worried about is the magnitude anyway, right? We're trying to find an EMF. EMFs can be negative. It's just we usually don't care about it, so leave off the negative sign for now. You get the sine of theta, but we're not done. What else? If theta is a function of time, what do I need to apply? Chain rule, right? Derivative of a function is derivative of the function times the derivative of the argument of the function, right? The argument of this function is itself a function of time. Therefore, we have to take its derivative. So I get d theta dt. It could be a complex function, it could be a simple function, but if theta is a function of time, you gotta apply the chain rule. What is d theta dt? I realized 1600 might have been a while ago. What is that? What is dx dt? Linear velocity. Because x is your linear position. Theta is your angular position. We're expressing this in radians, right? So what is d theta dt? Angular velocity. Symbolized commonly by an omega. Lowercase omega. So that's NAV omega sine theta, where omega is the angular velocity of however you're turning this, right? Here is a generator. All right, we alluded to that last time. But here's how it works. You rotate some coil with an angular velocity omega. And you get out of that a current. You get out of it an EMF, which then turns into a current as long as your loop is closed. We talked a little bit about, this is a DC motor, so we're gonna have to break the circuit. You did this in lab the other day, right? How did you break the circuit every half cycle in your simple motor activity?
Wire coating.
Say what?
Coating the wire.
Yeah, you just sanded off the coating on half of it, right? In effect, you made a really crude commutator. I can't draw a commutator. Go look one up online if you want to see what it looks like. It's basically a physical structure in the coil that breaks the current every half cycle. But this is the EMF that's produced. Now, it's not constant. Right? There are all sorts of electronic devices that you can then use to make it constant, rectifiers and diodes and things of that nature, which better left to your engineering classes. That's not my area of expertise. But you have an EMF that's produced. This is how electricity is made, right? But we can go the other way as well. Just like we saw with that illustration of pulling the bar, that I can pull the bar and get a current, but if I change the field, then I can move the bar on my own. You can do the same thing here. I'm assuming that somebody is turning this coil with some velocity omega, either a hand crank, if you're really old school, if you're trying to start a car in the 1920s, right? Or a gasoline-powered generator, if you are trying to get your freezer, keep freezing in the middle of a hurricane, right? Or whatever you have. You are turning a crank to produce electricity. But this can also go the other way. I could, instead of changing the position of the armature, change the field, right? Then I can produce motion, right? So this works both ways. A generator, you put in motion, however you choose to do it. You rotate the coil, you get out electricity. But an electric motor is the exact same thing. Only you put in electricity and you get out motion. Right? They're the same thing. And that becomes important when we start talking about back EMF, which we'll do briefly right now, but more in depth next time. So here's the crux of this. Rotate something in a magnetic field and you get an EMF. Change a current through a coil in a magnetic field and you get out rotation. Right? That's all well and good. The problem comes in that there are lots of systems in which this happens simultaneously. Think about something as routine as a vacuum cleaner. A vacuum cleaner has to rotate a brush, right? It has to create suction. It does this with electric motors. So you plug in your vacuum cleaner to the wall, you turn it on, electricity flows into the motor and produces motion, right? So to get that motion, you have to have a field. So there's a magnet inside that motor. That's why magnets are so, one of the reasons motors are so heavy, because they have large permanent magnets inside them. You have a magnet, you have something rotating, right? You made it rotate because you put in electricity. But you now have something rotating inside a magnetic field that's producing its own EMF. And because of the way nature works, GH changes, it produces an EMF that opposes the EMF of the incoming electricity, right? So it strives to find a balance. We're going to get into this more next time, but for some of you who were raised in older houses, if you turn on a vacuum cleaner, your lights dim, right? And this is exactly why. We'll get into the details later, because as the thing starts to rotate, right, it actually opposes electricity coming in. It opposes, I should say, it opposes the EMF that's putting electricity into it. It finds a balance, but we're talking about the idea of a back EMF. So that turns out to be really, really important for engineering applications. So we're going to get more into it next time, but I want you to see it this time. Generator and motors are both described by this equation. It depends on what you're putting in. You put in electricity, you get out motion. You put in motion, you get out electricity. But in all cases, you have to find balance because you get both of them. All right, that's enough talking. Let's take it.